look at today are some more ways that we can do limits algebraically. Now, this first method we did last year, and this is where you change this by doing what? You remember? Multiply by the conjugate. That's exactly right. So what is the conjugate here? Radicals x plus 1, and then you do plus 1. Same thing on the bottom. Do you remember what happens when you multiply by the conjugate? You get difference of two squares, exactly, because what happens is this is a minus b, and this is a plus b. All right? We're on the same page we were on yesterday. It's like the second page. All right. So when we do difference of two squares, we get a squared minus b squared. So if you want to write this down, you may. I personally would not include this step, but this does help some people. What are you going to get when you square those two things? You lose the radical, and the ones cancel, so you end up with x. Can I go and skip to that step? Square the square roots, you get what's inside, you'll get x plus 1. 1 squared is 1, the 1's cancel, so you've got an x in the numerator. Alright, then what will happen? The x's cancels on the top and the bottom. So am I to a point where I can do direct substitution? Yes, I can. And if you substitute 0 in for x, what are you left with? 2. You plug in 0 here. 1 plus 1 is 2. So we get 1/2. Alright, questions about that? Alright. Now, the two special trig limits. You actually explored some of this in homeworks 2 and 3 on the homework when they had you do a table. And you, by doing the table, learned that these two special limits happen to be 1 and 0. Now, just to prove that to you, if y'all will get your calculators out, whether it's an 84 or an Inspire, it doesn't matter. Let's just look at these real quickly. And let's see if you believe the fact that those limits actually are 1 and 0. Let's just kind of do that to prove it to us. So on the Inspire, put a graphs page in there. Now how do I get the fraction template? Control divide. So I'm going to do sine of x over x. By the way, what would be the domain of this? X can't be 0, right? Is sine of x defined everywhere? Just plain old sine of x. Yes. Its domain's all real numbers, isn't it? So why does this have a domain x can't be 0? Right, it's rational. It's rational. You said the denominator not equal to 0. That's why. So let's see if the calculator does that for us. And I bet the answer to that is no, right? So press enter. Okay, and we get this nice little graph. But look at what's happening here at 0. I think clearly we see it's getting closer and closer to what? 1. But we know, since the domain of this is x can't be 0, we know that there's probably an asymptote or a hole right there. Now do y'all see an asymptote? No. So I'm pretty confident there's a hole right here. But regardless, it's obvious from the graph, and I've already done a table for this once, that this limit is equal to 1. And that's why. We can look at the graph and the table and kind of show ourselves that's going to be true. Now, this is not a proof. To actually prove that it's 1, you have to do something called an epsilon delta proof. And we may look at those later this year because if any of y'all take first year calculus next year at a university, most college professors have you do epsilon delta proofs. They have not been in the AP curriculum for years, so normally we don't get into that, but we may look at them a little bit so that y'all that are going to have to take that next year will have some background. All right? So what does all this mean? You got to memorize that. You got to know that one limit. All right? All right. Now, let's look at the other function that they had. So let's do a clean screen here. I'm going to do home and do number 2 here. Control divide. And what's the other one? Like 1 minus cosine of x over x. Does that have any domain problems? What domain problems does this have? X can't be 0 on this one, right? So what do you expect to happen at x equals 0? Or probably an asymptote, one of the other normally, right? Okay, so let's see what happens. Do you see an asymptote? Nope. But look here at 0. From the right and from the left, what is that approaching? 0. But we know more than the calculator does. We know x can't be 0, so we know here at the origin, there really should be a hole there. But what this tells me graphically, and you've already done the chart for this, what this tells me is that this limit is equal to 0. This is another limit that you need to memorize. So we have 2 right now. Okay, so what are we going to do with this? Well, if you'll go back to the handout, we have to use these 2 limits to solve other problems. Y'all are just going to get your feet wet on this today, and we're going to look at more of it tomorrow. But let's just take a couple of them like this one right here. The limit is x approaches 0, sine of 4x over x. Is this similar to this limit rule right here? How is it different? All right. How can I change that or adjust it? Good thought. But remember, with trig functions, you can't just do that because we have all those identities. Remember how like sine of 2x was 2 sine x cosine x, and you have all those identities, so you can't just factor a 4 out. Good thought, but that's not exactly what you do. No, you don't want to square anything. I don't think that'll work, but oh, I see what you're saying. You could write that in terms of sine of 2x. There is a way to do it, but we're going way too complicated here. There is an easier way to make this look more like this. Where? Yes. if I do something else, though. Yes, if you put a 4 in the denominator, you need to put a 4 in the numerator. And you can either put it in the front, like Audrey suggested, or when I do it, I usually do it over here to the side. But what she suggested would work as well. And then here is what happens. Not only is this limit equal to 1, but anytime this matches up with this, that limit is 1. Like if it's sine of 2x over 2x, sine of 3x over 3x, those limits are 1 as well. Now, a little bit from last year, we haven't done this in a while. Now, we said that limit was 1. Do you remember what the limit of a number is? The number. So that answer is 4. Okay. Now, we will see more of this tomorrow. Let's just get your feet wet because we've got some other things to look at. But that's kind of where you go with this. All right, any ideas on the tangent one? Okay, right. A couple of y'all said it's sine over cosine. Now what? Multiply by the reciprocal. All right, that sounds like a plan. I'll buy that. Now what? Um, yeah, keep in mind, Lakeith, you don't want to try to go too complicated on these. Okay, they're not intended to be that complicated as far as squaring and doing really fancy identities. All right, so what you want to do is you want to make it look as much like this as you can. And so I heard someone say to do what now? It is, because we have what property from junior high says that cosine of x times x is the same as x cosine of x? What property says that you can just switch those? What identity? What's a property? It starts with C. Not communicable, but when people that go to college commutative, right? It's the commutative property, remember? All right. So the commutative property tells us that it is legal, like, to switch these around. Cosine of x times x is the same as x times cosine of x. That's a commutative property. So what did y'all say this limit was? 1. Now, how am I going to do this limit? It is, but how do I? You're right, but how do I calculate that limit? Say that again. Yeah, direct substitution, right? Can't you just plug 0? You were trying to make it too hard. Yeah, you just plug 0 in. And we can get cosine of 0 either from the graph or the unit circle. So what is cosine of 0? 1. So the answer is 1. So we'll look at a few more of these tomorrow. But in a nutshell, I have kind of given you a brief overview now of this entire section. Really, the only thing that we're adding from what we did last year is that we didn't do any of these trig ones last year. But that's about it. Okay, everybody stand up for a second. Y'all look conked out. So stand up. Come on. Stand up and stretch. Now, what we're going to do here is we're going to formalize a little bit more some of the rules of limits. Some of these rules we've been using, but I want to make sure that that we do this a little bit more formally. So the first thing is we have said that for many well-behaved functions that we can just do direct substitution. Now, when we do it by direct substitution, you're going to see this word more and more called continuous. You're going to see continuous and continuity a whole lot in the next few sections. But basically, the reason you can do direct substitution is because the functions are continuous at that point. That's why you can do it this way. So, what we basically have learned is that, for instance, if I have the limit of a number, what did we say that was going to be equal to? The number. But is it the 3 or is it the 7? The 7. Limit of a number is a number. If you have the limit of x or some variable, normally you can just plug the number in and get the answer. Now, all of these properties down here basically tell you that if you know values for two different limits, if you know those values, you can multiply them, you can add them, you can subtract them, you can do them to powers. Now, that may seem kind of weird that they throw that in there, but this is actually going to be on the homework. If y'all will look over on this page here on the bottom, here's how they're going to test you on this. All right, I have some generic function, and its limit at x equals c is 2. Here's another generic function, and its limit is 3. How do you think I'm going to calculate that first limit there? 5 times 3. Now, here's technically why that works. Do you see how this is a constant? Technically, the reason this works is I can take that 5 on the outside and just do this limit here. And by the definition, they've told you that limit was 3. C just means some arbitrary number. C could be 2 or 10 or 100. It's just x equals C. It could be some generic number on the x-axis. So like on this one, if I just wanted the answer, what would I do? Two plus 3 is 5. But the reason that works is because we have a limit rule that says that this expression is the same as finding the limit of f of x and then adding it to the limit of g of x. All right. No, I just want to make sure you understand where it's coming from. So no. All right. So what about this next one? What would I do? 2 times 3. All right. Now here again, the reason that works is there is a limit rule that says that this is the same as taking the limit of f and multiplying it by the limit of g. This is actually harder to prove than you would think. You have to do these epsilon delta proofs, and that's actually really hard to prove, to be honest. It's harder than you would think. And what do you think this one will be? 2/3. So are we okay on that? All right. Now on the top of that page, what in the world do you think this is telling you with these trig functions? What does all that junk mean? Yeah. What are they basically doing here? So plugging the constant number in. So what do we call that in limits? Direct substitution. They're just telling you you can do direct substitution with trig values. Well, but you gotta realize in math, we have to have rules for everything. That's just the way math is set up. You know. Well, that may be true, but that's just the way. That's why math is what it is. It's not that bad. All right, let's do one of these trig ones. This one you can't do from the unit circle, at least at the quadrant angles. If I substitute 7 in here, I get secant of 7 pi 6. Ooh. All right. Now, secant, what is that, by the way? Cosine. So, let's recall from last year the way most of y'all would have done cosine of 7 pi 6. What most of y'all would have done is multiply that by 180 over pi and make that degrees. And that's 210. And so you would have done cosine of 210. Alright, so what quadrant is that in? Third quadrant. Now, let's say you forgot all those fancy rules we learned last year. You could still get the answer without knowing any of them. Let me show you how. Alright, now you remember when we did this in our head, the next thing we did is we said, okay, well, what's the reference angle? It's 30. Now here's why. If I'm drawing that angle, I'm going to go 90, 180, and then how many more degrees? 30, right? Right? Then you ask yourself, what is the cosine of 30? Okay, well, let's say you have forgotten that. Okay, if you have forgotten that, there's two ways to remember it, two or three ways. One is you can go back to geometry, freshman year for most of y'all. And you remember when we did 30, 60, 90 triangles? 30, 60, 90 triangles, the rule was if the short leg was 1, the hypotenuse was 2 times the short leg, right? And then the long leg was radical 3 times the short leg. So based on that 30, 60, 90 triangle, what's cosine of 30? SOHCAHTOA. Radical 3 over 2, right? Alright. Now we have to do all students take calculus. What? So we're in the third quadrant. What's positive? Tangent's positive, so that means sine and cosine are negative. Okay, then we need to flip this, do the reciprocal, and there's the answer. Alright. So the trig stuff, I mean, I know we haven't done it in a little while, but you are going to have to start refamiliarizing yourself with this. All right? But, and see, technically, I could have gotten that from the picture because this is negative and this is negative. And if I'd have done cosine, it would have been adjacent over hypotenuse, and I would have gotten the cosine from the picture if I'd wanted to. All right. Go back a page now, and we need to talk about a limit of a function involving a radical. Doesn't really look like it's that big of a deal, but it actually really is. All right, let's read what this thing says. It says, let n be a positive integer. The following limit is valid for all c if n is odd. All right, so let's stop there for a second. What they're saying is, if I have a cube root, if I have a fifth root, any odd root, they're just basically telling me I can do direct substitution. Why? Why can I do direct substitution for all cube roots and fifth roots and seventh roots for any real number? Why? What's special about cube roots and fifth roots that's different? You can do what? You can take what of a negative number? You can do a cube root of the fifth root. So in other words, if I could take cube roots of positive and negative numbers, what is that kind of talking about? You don't end up with imaginary numbers. So what is the domain of it? All real numbers, right? And you're going to learn later that cube roots and fifth roots and seventh root functions, they are continuous everywhere. So this is basically telling you you can do direct substitution for any odd roots that you have. But then it says if it's even, you can do it as long as the number is bigger than 0. Okay, interesting here. So like if I have a square root, I can only plug the number in if that number is bigger than 0. I can do 0.1, I could do 0.5, I can do 1, I can do 100,000. My question though is, why can't I do it? And this is the one you always got to worry about. Why can't you do it at 0? What doesn't exist? Sure it is. Square root of 0 is 0. Good idea. You're on the right track though. Something doesn't exist there. Okay, so we don't know analytically then why. So what do you turn to if you don't know how to do it algebraically? You look at the graph. Okay, so will y'all graph that for me? Graph the square root function. So if we don't know how to do a limit algebraically or analytically, what's the domain problem with it? Well, it does. Yeah, your calculator's tricking you. There's not a hole either because I can do square root of 0. Didn't you get something like this? It's not an asymptote either. Okay, well let me make sure that yours looks right then. And so let's pull this up. So I'm going to do home number 2 I'm going to do square root of x, enter, and you get that right there. No. I'm just saying that there is a dot right there. Why isn't the limit x approaches 0, why can't I just plug 0 in and say that? Say that again. Exactly. The limit from the right is 0. Agree? But there is nothing from the left. There is no graph. There's nothing. So, the limit x approaches 0 from the left of this doesn't exist. Wait a minute. So, since the limit doesn't exist from the left and the right, what does that mean? Since they're not the same, right? We have a limit from the right. We don't have a limit from the left, so they're not the same. That means that doesn't exist. That's why you can't do direct substitution on the square root functions when it's 0 or if the numbers are negative. Alright, so try to do some more of these homeworks. We're going to finish this up tomorrow. We do have a quiz.